Hello everyone, my name is Miguel Palacios from the Innova Research Center. I'm going to present our work detecting and identifying global visual novelties in driving scenarios. This is a joint work with my colleagues Jair Escalante and Enrique Zucar. First of all, I will present our motivation. As a real-world and safety-critical application, an automated driver system has to operate in environments in which driving scenarios show continuous motion and dynamic interaction among traffic elements. These conditions can lead to unpredictable anomalous situations that are not registered previously, so safe navigation could be compromised. In this work, we focus on the problem of novelty detection in images captured by a front camera in these scenarios. On the other hand, most prior work on visual novelty detection points out novelty instances, but uh, does not provide additional information that can be used in the decision-making process. We propose an approach that is able to detect global visual novelties, considering a complete descent as the area of interest, at the same time that it identifies the type of novelty. As a brief background, novelty detection is a process of identifying if new data does not belong to the previous observed patterns. So, in this context, novel data is not available. In the right side, we can see the general training and testing phases for both classifier and novelty detector. While the classifier has training data for the entire classes, novel data for the novel detector is not available. It is worth noting that in testing, when a novel sample is presented, the classifier will assign a ground class to the sample. The novelty detection, it is closely related to outlier detection and anomaly detection. In this slide, we can see the general overview of the two-step method proposed. For the visual novelty detection task, we use a generative adversarial network extended with a down encoder as generator. Reconstruction is used as novelty signal, and as the GAN model is training with normal data, it is expected that error reconstruction for novel samples should be higher than the error for normal data. So a threshold is defined in order to detect the visual novelty instance. On the other hand, if a novel instance is detected, the type of novelty is obtained with a support vector machine using the structural similarity index components, the mean and square error, and a middle layer of the generators of network. In specific, global visual novelty detection is based on a GAN model. A GAN model is based on two subnetworks, a generator and a discriminator. The generator tries to fool the discriminator and tries to produce real samples. On the other hand, the discriminator tries to estimate if a new sample is produced by the generator or comes from the real samples. Competitive training is captured by the adversarial loss. Additionally to this loss, we introduce a generator loss that combines visual and pixel-wise information. Visual information is captured by the structural similarity index through the luminance, contrast, and structural components. And pixel-wise information is captured by the mean square error. Thus, the final loss for training the GAN model is computed using the combination of the adversarial loss and the generator loss. In this slide, we can see the architecture of the generator and discriminators of networks. The generator is a convolutional denoised autoencoder with 4 convolutional layers and leaky relog activations. For the decoder, we have 5 deconvolutional layers with relog activations and the last layer with sigmoid activation. The discriminator has 4 convolutional layers, 1 flattened layer, and a final node with sigmoid activation. Novelty identification. For novelty identification, we propose to use a support vector machine approach in which inputs like feature map, similarity structure index components, and mean square error are used as features to train this model. The support vector machine is training with a radial basis function kernel. In general, we aim for a model able to detect the novelty type with only a small number of samples. This is because the novelty context. Experimental results. We use the 4 dataset that includes images captured by several vehicles in different driving scenarios. 3 scenarios of normality are considered for experimentation. The table 1 shows the general description and the right figures in the right side show visual examples of this scenario. We can see that the scenario 1 contains cloudy scene with mainly highway views. The second scenario contains also highway views, but add visual information in airports scenarios. Finally, the third scenario considers more variations where the environment is not a highway, so buildings, vegetation, and less lanes that the highway, producing high visual effect in which also random objects are more close to the camera view. Also, we can see the number of training samples available for these different scenarios. Two types of novelties are considered. The type 1 corresponds to challenging illumination condition, mostly observed when the vehicle is into, under, or leaving a bridge or tunnel. The type 2 corresponding to large objects. These include vehicles too close to the camera view or large bridge. This type of novelties were selected because are close related to real critical situation. For example, a large object close to the camera view can be produced by a rear-end collision. Table 2 summarizes the results for the 3 driving scenarios in terms of the AUC computed from 5 training testing phases. The UAC is computed based on the generator loss equation of the test dataset. A baseline autoencoder is used for comparison. AUC is based on the mean square error in this case. As we can see, GAN model surpassed the baseline autoencoder in all the experiments. We know that while the GAN model can support visual variations of the normal driving scenarios without impacting its novelty detection performance, the baseline autoencoder decreases its performance when the normal driving scenario is more challenging. This behavior can be observed in the third scenario. For novelty identifications, because of the novelty context, we maintain a constraint on the number of samples. Only 20 samples of each type of novelty are used to train a support vector machine. We present accuracy for 5 training testing phases for each scenario. The graphics shows the accuracy for each scenario when combinations of the feature map computed by the middle layer of the generators network, along with mean square error and structural similarity structural index components like luminance, contrast, and structure are used. As we can see, any combination, excluding the scenario 1, only using the feature map, the red line in the graphics, obtains a lower performance than when used in combination with one or more components. Best performance is reached when the contrast structure and mean square error, the green line, is used in combination with a feature map, reaching an average of 92.7%. As a conclusion, a two-step method for global novelty detection and novelty type identification has been proposed. We use a GAN model in order to detect novelty instances. A weighted linear combination of a structural similarity index and mean square measures is used as part of the loss function of the GAN model, and in testing is used as novelty signal. This model reaches an average AUC of uh, 0.99 on the other hand, we use for novelty identification as a support vector machine classifier, along with feature map, mean square error, structural and contrast components of the structural similarity index are successfully applied as input features to this model, showing an 92.7% of accuracy for this task. The method is applied to images of real driving scenarios where the complete scene is analyzed. Additionally, we have developed a dataset for the evaluation of global novelty detection algorithms in driving scenarios. Future work considers the extension of the model for local novelty detection and experimentation in driving scenarios with video datasets. Finally, some of the more important reference, and thank you for listening.